That is a good approach. Where are the Safari people? Only one, two. Okay. You got the latest slide type. Okay. Or both.
For A, you send them like 20 minutes.
Yeah, that's right. Well, both of them are latest. Do you have something to charge this? Okay, that phone will work. My own computer, I forgot to charge. Excuse me.
You don't have the charger.
I don't have the charger though.
I have a charger.
Okay, if you have it, then it'll be great. I mean, it's not urgent. It's not. But I want it to last.
I have two chargers.
Okay. Yeah, maybe we can charge mine and then.
I don't have a Mac. So.
You don't have a Mac? That's probably reasonable. Okay, thanks. Okay. Always warm here. Thanks. We can take it once it's a bit charged. Okay, a second one. Redundancy. What is this? Okay. How do we clean it? Is it easy? With this or?
Maybe that thing.
Oh, okay. Go ahead. I'll let you decide.
Are you gonna use it?
I might. I don't know. That's why. I don't want to clean it on the critical path. I may not also. Let's see. Normally the previous course should clean it, but. Oh. Everything is okay online. We'll start in a minute. Okay. All good time. Yeah, sure. Now you can hear me, right? I didn't do anything to this. You can hear me? All good? Yes, I'm speaking. How about now? Okay, yeah, it takes a while. Yeah, okay. Oh, it looks much better. Thanks. Clean. Thanks. Yeah. Okay. That's good at charging. Okay, let's get started. We have a smaller crowd today. Is there a reason for that? Holiday soon? Not yet, you know. 18th is when the holiday starts now. Okay, anyway. I hope people who are not coming to class are following online. I know some people always come to class. That's great. It's good to have people who interact and express interest. Okay, so today we're going to jump into systolic arrays. And this is probably the last model we will cover in terms of execution paradigms. Last week we've covered GPUs, previous week SIMD. Were they interesting? Yeah, so we covered a lot of things. I mean, we may cover multi-threading at some point, but let's see, we don't have a lot of lectures in this course. So if you're interested in multi-threading, probably computer architecture is the place to go to. But before I start, Zoom always plays tricks. Okay, I will tell you that we have a lot of research opportunities. If you're interested in doing research and the topics we covered, and also a lot of topics that we didn't cover, like a lot of topics in computer architecture, memory, storage, security, systems, and also bioinformatics, please feel free to contact us. We have a lot of opportunities. You can, of course, take our seminar course. Some of you are doing it. Computer architecture course, which is more advanced. A seminar course is more paper reading. You can do the readings and assignments. But essentially, if you want to do research, talk to us. And they're us, meaning me, Mohammed, other people who are part of the group, Konstantinos here, and there are other people who come sometimes. There are many exciting projects and research topics. And again, I'm not going to read all of these, but we do a lot of work on new future computing systems. I'm especially interested in new execution paradigms like in-memory computing that are different from everything that we're talking, more memory-centric computing paradigms. And also we do a lot of work on hardware robustness, safety, security, etc., and heterogeneous systems. Yeah, okay. And also architectures for important workloads, hardware, software, co-design. So there's a limited list. So if people are usually ask us like, okay, if I want to do a thesis with you, what do I do? Basically, talk with us is the right answer over here. You can, of course, go and look at what we do. This is our publications list. There are a lot of things over there that you may want to look. There's also a somewhat up-to-date thesis list, but it's really not up-to-date in the end because it's very hard to keep it up-to-date. It's more important to do the work than keep the thesis list up-to-date. So talking with us is the best way. And maybe we can recommend some papers, etc. And you can learn about us. I mentioned this in the first lecture, but there's a lot of information on our website about our group. And these are some people. Look, Konstantinos is there in 2020. That's him. A younger version. Yeah, okay. But basically, we have a bunch of things that describe our research. These are really newsletters that we release almost every year. Well, one of them is coming up in 2025. As you can see, based on last time prediction, you can predict when it might be coming next. And we have a lot of videos, but you can talk to us also. So there's a lot of material on what we do, our mindset, etc. And if you're interested in doing a PhD at some point, we do that also. And I'm proud of all my PhD students and postdocs. I think postdocs is not a complete list, but we need to complete it at some point. The font size will become a little bit smaller then if we do that. Yeah, and they've done a lot of outstanding work, and right now they're leaders in academia and industry. Okay, now if you're an ETH student, you don't necessarily need to apply. Talking with us is the easiest way. But if you're an online person somewhere else other than ETH, this is how we can get to know you. If you're at ETH, you have kind of an advantage, clearly, right? Because you're taking this class, we can see you, we can talk more easily. But if you're not at ETH, then it's harder to do that. So you need to apply in that case. And the application site is already there. Okay, with that out of the way, and I'd encourage people who are interested in doing research to try doing research. If you are not confident, let's say, it's okay. Like when I read my first research paper, I didn't understand anything, which is fine. I mean, that's how you learn, right? Yeah, the learning curve is high, but once you actually overcome some activation potential, you can do a lot of exciting things, I think. So in the end, there's no pain, no gain. you got to have some pain so that you can actually get to a point where you can actually lead the field, right? It just doesn't happen. I mean, unless you're absolutely randomly lucky in some way. That also happens, but the probability of that is very, very low. Okay, so now we've covered everything up to here. I'm not going to cover decoupled access execute. You can take a look at maybe we can premiere a very short lecture on that. I'm going to cover systolic arrays because this is a topic that's really critically important. Like in a sense, I'm a very principled architect. I like principles. And I've been covering systolic arrays since 2009 when I was teaching at Carnegie Mellon. And people were asking, why are you covering these things? Nobody does this. Today, a lot of people do it. Why was I covering this? Because I thought it was a principled architecture. It's very important for accelerating some workloads. And if you have a principled architecture, at some point, it could actually be beneficial. So I'm going to cover this. But now, today, is not 2009. Today it's 2025. So you'll see examples of real systolic arrays employed for machine learning, especially Google does that a lot, but there are other companies that employ it as well. Today, it's actually, when you do machine learning, it's really a combination of SIMD and systolic arrays, even at Google. Even though they started with systolic arrays, they added SIMD units also because they wanted to reduce the overheads. In fact, we will see that Google uses VLIW, SIMD, and systolic arrays in their TPUs. All three paradigms are there together. And then there's a host CPU that controls it. So there's all of these paradigms are also there. So basically what you learned actually is real in real systems, and you're going to learn a very important one, I think. Okay, so these are readings. This is, I mean, there's nothing required, but I would suggest reading this beautiful paper by H.T. Kung. It's not the first paper. He is really the inventor of systolic arrays, and he did this in 1970s with Charles Leiserson. And then this is a nice paper that summarized it. And then these are Google papers that actually introduced their TPU and also talk about some TPU2 and TPU v3. It has a Google bias, so be careful. Sometimes when I read some of these papers, I mean, I cringe because there are some things in there that are interesting. I can imagine NVIDIA people reading them also. Okay, it's good to think about that. Okay, so let's go into systolic arrays. Okay, basically, if you want to talk about systolic arrays, you have to think about general purpose versus special purpose systems, right? So clearly, we talked a lot about general purpose systems that can execute anything. These are very flexible. They can execute any program. They're easy to program and use, but they don't provide the best performance and efficiency on anything, essentially. They're good at average performance and efficiency. And then on the very extreme end, you have special purpose, application-specific integrated circuits. Maybe Cerebras is not the best example for this, but Cerebras has some special purpose. If you want to be really special purpose, you burn the program into hardware, right? That's the real ASIC in the end. And then you're very efficient and high performance for that thing that you burned into hardware. You don't have any control overhead. You don't have any instructions, let's say. Everything just flows, maybe. But it's very difficult to program and use, and it's very inflexible. You may run only one program or a limited set of programs. Now, this is more on the special purpose end because it's really unable to execute everything. And then you can basically think about where the other things lie. So some of these used to be very special purpose GPUs, but they became more and more general purpose by adding new things. FPGAs, you could argue they're actually general purpose, but maybe they're not good at executing everything, etc. So it's good to think about where do these things lie. There's not a clear spectrum over here, but this is definitely general purpose, right? And if you want to be special purpose completely, you just burn the program into the hardware. Okay, so systolic arrays are closer to this end, essentially. Basically, they're very special purpose engines. And they're really not like GPUs or SIMD, they're an execution model. Essentially, they implement an execution model called systolic computation. This is different from von Neumann, different from data flow, and different from what we looked at with GPUs like SIMD, SIMT paradigms. And they're initially designed as special purpose accelerators, and they're today used as special purpose accelerators also. And the reason they were designed was actually for convolutions, filtering, pattern matching, special purpose matrix vector computation, image and vision processing, signal processing, pattern recognition. And machine learning is essentially all of those today. That's why they've been successful, let's say, with the rise of machine learning. So today, they're currently heavily used in machine learning in specialized accelerators. But their general execution model can be generalized. So we will actually generalize their execution model to more pipeline processing, not the pipeline hardware, but pipeline processing, pipeline parallel programs. And we will see that these could be useful for other purposes as well. And I truly believe that. I think we need to look at more of these systolic computation examples in other programs as well. Okay. And we will see some of this later in the lecture. So what is the motivation for these? Essentially, the original motivation was to design an accelerator that is simple, regular, because that's one of the benefits of designing an accelerator, right? So you can, if you're simple and regular, you can do things much more efficiently, perhaps. So you keep the unique parts small and regular. You want high concurrency, high performance in an accelerator, clearly. And you want to tolerate the memory issues. So you want to balance computation and memory bandwidth. And we're going to talk about that. We're going to talk a lot more about memory when we go into the future. In fact, in this lecture, I added some slides that talk about memory also. So basically, the idea is to replace a single processing element with a regular array of processing elements and carefully orchestrate the flow of data between the processing elements such that you have tightly coupled computation that happens in the processing elements, and you fetch the data only once. Computation happens in this, let's say, array of processing elements, and then you write the result back to memory. This way, you don't need to fetch everything back and forth from memory. Okay, basically, collectively, these processing elements transform a piece of input data before outputting it to memory. And their benefit is to maximize computation done on a single piece of data element brought from memory. Makes sense, right? And you can also think about it maximizing the arithmetic intensity of the program. You bring 1 byte of data and you do a lot of operations on it, and then you push it out to memory. That's what you would like. Of course, it works if you have that sort of computation. So this is a picture from the paper that I recommended from H.T. Kung. Essentially, he motivates us this way also. You have a processing element and memory. And if you have only one processing element, you may actually need to keep fetching data. You do something, you fetch data, you do something, and you write back to memory. You fetch data again, you do something, and then you write back. Basically, in this picture, you have a vector of processing elements or one-dimensional array of processing elements. And this processing element does something to the data, passes it on to the next processing element, which does something else, passes on to the next one, next one, next one, next one. And you basically put it out to memory after a long time. And in this case, you basically multiplied the millions of operations per second by 6x because you have 6 processing elements, right? Okay, so that's the basic principle. And that's the real basic goal in the end. And H.T. Kung actually has done a lot of theoretical work on balancing I/O and compute needs. This is very important, actually, in my opinion. Today, we're very imbalanced with memory access versus compute. And he has done a lot of interesting work in this area. Okay, so if you, why systolic, basically? You can think of the memory as the heart. And you can think of the data as the blood. And you can think of the processing elements as the cells. And memory essentially pulses data through the processing elements, right? And this is how he motivates it also. Okay, so essentially data flows from the computer memory in a rhythmic fashion, passing through many processing elements before it returns to memory. And I've already said this, right? It's similar to blood flow. Different cells process the blood. And it can be many-dimensional, just like the blood flow. And we will see some many-dimensional examples too. So essentially, we've discussed this, why I've already said all of these. I think this sort of design satisfies those requirements, assuming your computation matches this sort of computation paradigm. Okay, I think I already said all of this. So you can ask, what is the difference from pipelining? It's actually pipelining at a different level, right? Not the pipelining that we saw. We're not pipelining instruction execution. We're really pipelining the flow of data across many different computations, right? That's the idea over here. But compared to pipelining we have seen, the difference is these are individual programming processing elements. They could be very, very powerful, basically. If you look at the pipeline that we have seen, it's a stage that can do only some part of the instruction. Here, these could be actually very powerful, right, if you think about it. Array structure also can be nonlinear and multidimensional. We have not seen that in pipelining. Pipelining is very linear, right? We're going to see multidimensional arrays that can communicate with each other. So it's really a processing paradigm as opposed to improving the instruction execution of instructions and partitioning them into smaller stages. It could be multi-directional and different speed also, the connections between processing elements. And processing elements, actually, if you generalize this, they can have local memory and execute kernels rather than a piece of the instruction. So that's the key difference from pipelining. Hopefully this is clear. It's probably obvious to a lot of you guys because you've seen pipelining and we've discussed it. Okay, let's take a look at an example, systolic computation. Again, convolution is one of the computations that's done. This is used in a lot of things like filtering, pattern matching, correlation, polynomial evaluation, and now machine learning, convolutional neural networks, for example, which is essentially using a lot of these concepts in the end. And many image processing tasks actually did this even before the rise of large neural networks, for example. And I said machine learning over here. So what is convolution? We're going to see this as an example later on. But essentially, you have a sequence of weights or vector of weights. You have an input sequence or a vector of input data. And you compute this, essentially. There's some multiplication. We're going to see this a little bit more soon. But let me motivate this a little bit. More recently, people have figured out how to use these convolutional neural networks to really do some computation on images and figure out essentially what the image looks like, right? You may be familiar with LeNet. This is one of the, let's say, smaller, not so deep neural networks that was introduced initially. And what you do in some of the layers of this neural network, there are many layers in a neural network. You basically do some convolution computation, and you do some sampling, and then you do some more convolution, and then you do some more sampling, and then you do some more computation, and then eventually you figure out what the output may be, right? It could be an A, B, C, D, E, F, whatever, yeah. Whatever you're trying to recognize. In this case, you may be trying to recognize letters or digits. In fact, LeNet was for digits. So basically, what is convolution in one of these steps? It's very simple in the end. This is an example. This is the input that you have. You could think of it as a two-dimensional array, part of an image, for example. And then you apply a filter to it. You apply some kernel to it. So these are the essentially the weights. This is the input. These are the weights. And you apply it to different parts of the image. Yeah, in a sense, you convolve the image to an output. Right? That's the idea. And you can see this is basically doing that. The filter goes through different parts of the image, and it's applied. And then you compute every single output element. Makes sense, right? Clearly, you could do this with the matrix multiplication also, and we're going to see that. Okay. I mean, I don't need to talk about a lot of things over here. Okay, so this is another example. I like this one because you could compute the values if you're interested. I didn't do that, so there might be errors here, but you can do it, I think. I hope it's right. I think I did for one, and then I didn't do it for the rest. Okay. Okay, and this is, if you're interested, this is actually Lynette. Jan LeCun has, he's one of the inventors of the deep neural networks. Has a website where he actually talks about how this works, etc. We're not going to talk about that. But again, if you look at this convolution operation, what you're doing is you have some input features, input data. You have some filters that look like this, and they could be of different sizes. We're showing small sizes over here. And then you want to compute some output. And the computation is you take these input features and essentially convolve them, multiply them with the convolution filters. And each input over here is the multiplication. So you can actually do the computation over here. If you multiply this, let me see. Yeah, essentially you can follow the green ones over here. This output over here is really an output of these three different filters applied to that element, or these parts over here. Hopefully that makes sense. In fact, you can do the computation perhaps. So what we're doing is really multiplying this and this. And if you do that, you get, I guess, 2 to 7. If you do that element by element multiplication, right, you get 7 in the end. If you do this multiplication, you get 3 more, 2, 1, and these are 0. So the multiplication gets 0. And if you do this one, you get only 2. 7, 3, 2 should be 12. Okay. Hopefully that made sense, right? And then you apply it basically for every single element. This one moves over here so that you could compute this element. All of them move over here. And also, if you want to compute this element, this filter moves down here. And all of these filters move down. And then you do the same multiplication. And then if you want to compute this element, this filter moves down to this lower quadrant over here. So hopefully it makes sense. And you can hopefully verify this. In the first iteration of the slide, we had some error. So that was a bit annoying. But this should be error-free. But this is one way of doing computation of convolution, right? Another way of doing computation of convolution is essentially what we saw, matrix multiplication, which is very well done in GPUs, for example, potentially. You could basically translate this convolution into something that looks like this. You basically have these filters laid out horizontally as a vector. This is the other filter over here, which we didn't look at. And then you also look at the input features laid out horizontally, like this, right? So you take this, that's one horizontal, and then you take this, that's another horizontal, etc. Well, in that case, vertical. Depends on which one you do first, right? One of them can be vertical, one of them is horizontal. And then you basically multiply this vector by this vector, and essentially you get the same thing at the end. Hopefully that makes sense. So you could use a systolic array to do something similar to this, or you could use a GPU or a systolic array to do something like this also. So it's good to think about transforming computation also. We're going to look at a systolic array that does something like this first. Make sense? Okay. So I think it's also motivational, and that's one of the reasons I want to talk about research at the beginning of this, because the computer architecture has actually played a lot of role in machine learning. Sometimes machine learning people don't realize that. But basically, the reason AlexNet got developed was because some folks at the University of Toronto, and you will see who those are, took an architecture course, parallel programming GPUs course, and they basically figured out how to develop the implementation of a deep convolutional neural network, how to train it, such that it can provide much better accuracy in recognizing images. We're talking about 2010, and they went and published this paper, which is a very important paper. It's essentially the ImageNet, AlexNet paper, which won the competition of recognizing images. Right? We're talking about 2012. And after this, actually, this is probably the turning point where after which neural networks really took off. After this, there are other people like GoogleNet. Google developed this GoogleNet, which basically made things deeper and deeper. And then other people developed other things. Essentially, if you look at the history, this is the AlexNet paper. Previously, people were using some shallow networks, etc. And with the deep neural networks, they reduced the error in classification of images significantly, as you can see. And over time, people added more and more layers to these networks, which are essentially doing a lot of convolution and other stuff. And today, the accuracy is better than human. Yeah, I don't know if you believe that. Yeah, these are error rates, basically. A 28% error went down to 3.6% error. Of course, this is all depend on the image data set, right? So maybe difficult images, humans are much better. That's why you sometimes go to a website and the machine asks you to check what is this in the image, and they train neural networks based on your responses, hoping that you actually gave the right response. So if you want to confuse them, give the wrong response all the time. Say it again. Yeah, maybe. Yeah, as long as you can tolerate that, right? Okay, so there's a lot more literature on neural networks, but that's not the purpose of this. But the key thing is there's a lot of convolution that's happening. The blue layers in these different networks are convolutional layers. So it's an important computation. There are also other computations which we're not going to go through. Okay, so let's take a look at how systolic arrays execute a simple convolution. Basically, this is, again, a copy-paste from the H.T. Kung paper. Essentially, we're going to see how a systolic array can be designed to execute this multiplication between two vectors. Right? It's a different type of multiplication, as you will see. It's not element-wise. Okay, so these are the outputs that we want. So if you look at the y vector, okay, let me go back. So we're computing yi. Yi is really a combination of a lot of things. W1, W2, WK, but then xi plus 1. So you can see that you're multiplying. And then y2 is like this. Assuming you have 3 elements in W, oh, what happened? And 3 elements in X, this is what Y elements should be. And you can verify that, but I think it's correct. And this is how you can design a very simple processing element or systolic array that can do this computation nicely. So let's take a look at each element over here. This is the processing element. And it's very specialized, as you can see. It stores the weight over here. Each of them stores a different weight. So this is how we combine them later. But assuming it stores weight W, it has 2 inputs, X in and Y in, as we want. And then it has 2 outputs, X out and Y out. Okay, let's take a look at what Y out is. Y out is basically Y in plus weight times X in. So you do this multiplication based on 2 inputs and you produce an output. That's the computation. It's very specialized, as you can see. And the other computation that you do is really passing the data to the other side. Essentially, X out is assigned X in. So there's no computation over there. You're just moving the data so that the next processing elements can get that data. Right? That's the idea. So you can think of this as a weight stationary thing, right? Essentially, weights are loaded, or maybe even hard burned into the hardware, but probably that's not a good idea today. But you have your weights in each processing elements, and you connect them like this. And now the problem becomes, how do you supply the data so that you get the right outputs, right? So you supply the data from the left, from these inputs. These are the X in. And it turns out you need to supply the data X1 first. And then you need to have let's say one cycle where you don't supply anything. And then you need to supply X2. And then one cycle you don't supply anything. And then you need to supply X3. We're going to solve this problem in the next slide by decoupling multiplication and addition. But if you do this, eventually at some point, X1 will reach W1, right? And then at the same time, when X1 reaches this processing element that stores W1, you supply Y1 also. So you need to orchestrate the data flow such that the data, the input data that you want comes to the right processing element at the right time, right? So you're kind of pumping data, if you think. You're pumping X's from here, you're pumping outputs from here. And when x1 comes over here after some number of cycles, because this is only 3, so then y1, there should be some signal saying that, oh, I actually get the output over here. And then this computes essentially what you want, right? W1 plus x1, and then passes the output, which is y out over here. Makes sense, right? So now we have W1, x1 over here. And then this moves over here, and then x2 moves over here, right? 1 cycle later. So now you have W1, x1 over here, and then you add to it W2, x2. Hopefully that makes sense. And then that goes over here. And when that comes over here, you get x3 over here. And then you add W3, x3. And you can also go through the other parts when you supply y2, etc. Yes?
So y1 at the very beginning far right is just like chaining the answers.
Yeah, exactly. You can think of that.
Y1 at the very beginning is basically just empty.
It's essentially empty. Okay. You can also think of it another way, right? You basically sample the output at the right times, right? Does that make sense? Yeah, you need to basically have a little bit more complexity to start the computation. But yes, you're really doing computation. So that's y1. And y2, you can actually do something similar. So when actually you supply y2 at the right place, and this becomes w1 x2, right? X2 will arrive over here. And when x2 arrives here, you should also input the y1, let's say. And then you'll compute w1 x2, right?
Like all the W's are in place and all the data is shifted.
Exactly.
Back and forth for y1, 2, and 3.
Exactly, yes. Yeah. Okay, hopefully it's clear. This is, I think, very clever. And it's very minimal hardware, right? You don't need much hardware for this. And H.T. Kung, in another figure, shows that how you can actually do things better. So you can actually implement adder and multiplier separately to allow overlapping of addition and multiplication executions. Again, I will not go through this in detail, but essentially, things are a bit decoupled over here. You have the multiplication, you have the addition over here. But you can see that you have, essentially you have W1, X1, and you add that to Y1 over here. But you need a little bit more complexity by adding latches to be able to decouple things. Again, I will not go through this. You can study it in the paper, but it's very simple concepts of by latching, you can decouple things a little bit. And do a lot more, get a lot more parallels. Okay. So basically, hopefully it's clear that you need to carefully orchestrate when data elements are input to the array, right? So, okay, let me go back to this. So this is very specialized. You can change this, right? You can actually make it compute something else. It doesn't have to be convolution. It could be something else. But convolution is a nice example. It could be also matrix multiplication, as we will see, something else essentially. So it could be anything if you think about it, right? It could be any specialized hardware over here, as long as you can orchestrate the data nicely. Meaning that your computation needs to be systolic or regular, right? So it's a different type of regularity if you think about it. SIMD, as we have seen it with SIMD and GPUs, it was some sort of regularity, data parallel regularism. You can probably map that over here also. In fact, you can. But this is still slightly different in the way it exploits that regularity. Okay. Basically, you need to orchestrate when data elements are input to the array, when you capture the output, essentially. That's the Y's coming from the right, if you remember. And this becomes more difficult or more involved. You need to be a little bit, let's say, careful if you increase your array dimensionality. This was a one-dimensional array, right, of processing elements. If you do two-dimensional, as we will see soon, you need to be a little bit more careful. But again, you need to orchestrate the data elements and output. It's become more difficult if processing elements are less predictable in terms of latency. Then you need to add stalls, etc. Not good for systolic arrays in general, but it's possible to do also. Let's take a look at matrix multiplication. Again, this is going to be simple again, but I think in general the concept is simple. But if you want to do this matrix multiplication A and B, and you need to define how you do it. There are multiple ways of doing it, actually. One way of doing it is basically saying keep the final result in the processing element. Another way of doing it is actually move the final result somewhere else, right? So there could be multiple ways of doing systolic computation, matrix multiplication. But again, where you're going to use a processing element that looks like this. This is actually a previous exam question, I think, in one of our DDCA exams, if I remember correctly. Basically, what we have is R. R is the result that we're going to have inside the processing element at the end of the systolic computation, hopefully. For example, for one element, R should be the dot product of this vector A00, A01, A02 with B00, B0, B10, B20, 0, right? That's essentially C00. Right? To get C00, you need to multiply this vector with this vector, right? This row vector with this column vector. Okay, so this processing element can actually accomplish by putting together these processing elements in a 3x3 setup and orchestrating the data movement of A's and B's into those processing elements. You can do the matrix multiplication. It's a very simple processing elements again. It's basically, let's start with what it passing data. It passes the left input M to the right output P, or you can think of it. It's basically this is the west input, and this goes the east output, right? P equals M, and it passes the, let's say, north input to the south output, Q equals N. That's easy. And then it accumulates in R. So a result gets updated as result, which is initially 0, plus M times N. It multiplies the, let's say, east and north inputs, right? Okay. We should have named these as north, east, west, south, right? That would have been better for explanation next time. Okay, so this is the systolic array that does it for 3x3, but you can generalize it, of course, if you want to. Essentially, you have this 3x3. Eventually, this 3x3 array will store C00, C01, C02, C10, C11, C12. And ideally, we would like to get this computation done. To be able to get that computation done, this is how you feed the data. You feed the first row of A matrix like this, A00 first, and this is the time, as you can see. At time 0, first cycle, you feed A00. In the next cycle, you feed A01. In the next cycle, you feed A02. And similarly, at time 0, you feed B00. And this one accumulates into it A00 times B00, which is what we want. And so this is easy. For the next one, you basically don't feed a 0 over here, because initially there's nothing here, right? You need to wait a little bit. And this one will come one cycle later, right? Assuming these are all single cycle operations. And that's true for this vector, this row vector also. Initially, you don't feed anything so that you wait for what comes from the Y dimension, right? So basically, you stagger the feeding of the row-wise input by one cycle so that things come at the right time when you have both data elements, right? And you do the same thing for the column inputs also, if you think about it. And you can convince yourselves that this will compute essentially this, right? Basically, in the first cycle, or cycle 0, this will be A00, B00. And in the next cycle, everyone will move by 1. So A00 will come over here. B01 will be here. So this will compute A00 times B01, which is, again, what we want. While that's happening, this will add to A00, B00, A01 times B10. And that's what we want, because you have A00, B00 over there, and then you add to it A01, B10, and you're accumulating essentially, basically, the dot product of those two vectors. Okay, so this is one way of doing systolic computation. It's beautiful, as you can see. And clearly, as matrix size grows, you can parallelize a lot more. But there are, people have developed other ways so that you don't keep the things idle, etc. So right now, there's a lot of idleness potentially here. Okay, makes sense, right? Beautiful. That's why it's principled, and that's why we taught it for many years. Okay, so if you look at H.T. Kung's paper, there's a lot of interesting things over here. He talks about different systolic arrays, two-dimensional we looked at, but it doesn't have to be two-dimensional. It could be diagonal, etc. I'm going to talk about actually, and there's a lot of interesting discussion over here that I'm not going to go into. He talks about the matching of memory speed versus computation speed, etc., which are really important things actually, and you need to do that in systolic arrays. So he has this nice example. I like this one. You can actually chain together multiple different types of systolic arrays to really form powerful specialized systems. For example, this particular systolic array is producing on-the-fly least squares fit to all the data that has arrived up to a given moment. So it could be ingesting data from a sensor, and you try to like model what kind of distribution there is in that data. And if you want, if least square fit is what you want, this is a beautiful, very specialized, let's say, combination of systolic arrays that can do that. So it could come up with a lot of interesting things. People don't do this yet, but I like it. But here you can see that you're orchestrating data such that the data comes at different points, and then you need to do some buffering also to do orchestration of data when you communicate between different systolic arrays. Right? Okay, if you're interested, there's a lot of interesting stuff in that paper. That's why it's recommended. Okay, so basically, that's it. I mean, that's systolic computation for you. The rest is going to be some generalization and also what's done today. But let's talk about pros and cons of this. Clearly, this is a very principled approach. The principle is really to efficiently make use of limited memory bandwidth. That was the reason this was developed, so that you actually do a lot of computation on a single element fetched, right? Or if you think of another way, you balance your computation and I/O bandwidth availability. You don't want I/O bandwidth to be a bottleneck, basically, right? Or memory bandwidth. I mean, people use I/O bandwidth and memory bandwidth interchangeably in the old days, especially. Okay, it's specialized. Computation should fit the PE organization and functions, and you can make it very, very lean, right? If you think about it, there's no instruction here, right? There's no instruction overhead. All of that is gone. If you look at a modern CPU, as we looked at, there's a lot of instruction processing overhead, right? No instruction. It's just data comes in, there's some operation done, and then data comes out. Okay, so basically, efficiency is very high. It's very simple design, high concurrency, and high performance, if you design it well, especially. So it's basically good to do more with less memory bandwidth requirements. The downside is also specialized. Essentially, that's an upside as well as downside, because now, what if your problem doesn't fit into it, or you cannot find a good way of fitting it? Essentially, it's not generally applicable because of this reason. Right? I mean, even data parallel paradigm, SIMD, is not generally applicable, right? If you don't have enough data parallelism, a GPU is very wasteful. A SIMD engine is very wasteful, because for example, if you're running scalar code on a GPU is terrible because you use only one SIMD lane. Right? That's exactly why when Cray designed its computers in 1970s, the Cray 1, for example, it was a heterogeneous machine. They had a vector engine and they had a scalar engine. And their scalar engine was faster than anybody's scalar engine at the time because they were very aware of Amdahl's law. They basically said, oh, we can parallelize our code, but in the end, our performance is very limited by how much we can parallelize. There's a scalar component that's going to bottleneck us. So let's make the scalar engine as fast as possible. So Cray was another person who was very smart in terms of designing simple computers. Yes? Well, not necessarily. You can design a systolic array without a GPU, right? It's actually used. I don't know if it's disclosed necessarily, but it's used in a lot of matrix computation units, for example, accelerators, even in CPUs today. Pieces of the CPUs, potentially. Yeah, usually matrix multiplication today, right? Yeah, exactly. Say it again? We're going to talk about that, yes. Yeah. Okay. So, okay, let me generalize it before we talk about that. Basically, they're very popular because of matrix multiplications that we do in machine learning. But it's not the only way. So other people, for example, we discussed last time, Cerebras, for example, they use SIMD units. Modern GPUs use, modern TPUs use a combination of it. I think modern GPUs also use a combination of things, right, with the tensor cores, etc. Yeah. So in the end, a combination of multiple paradigms are used. But I'm going to give you a very concrete example that explains things nicely from the TPU world. Because GPU world doesn't like to disclose a lot of stuff. Okay, so let's generalize it. Basically, you can do more programmable. So you can actually turn this into a little bit more general paradigm. You still need to orchestrate the data moment. Essentially, each programming element can store multiple weights as opposed to a single weight. In fact, weights can be selected on the fly. It could have a small memory, if you think about it. And this eases implementation because when you do adaptive filtering, you may want to use different weights, right? And when you want to do actually more general, you may want to do different kinds of filters. You may want to apply different kind of filters to the image because you're doing different operations, different on the image. So you don't want your weights to be, let's say, single or hardwired. And if you take this further, now each programming element can have its own dedicated data and instruction memory. Maybe, again, specialized, but data memory can store partial, temporary results and constants. And if you do this now, it becomes a general model, like stream processing, pipeline parallelism. More generally, I think I like calling it stage execution. Essentially, you divide your computation into stages, and each stage does something, and you can specialize your processing element for that particular stage, assuming you're executing that stage many, many times, for example. And then one stage passes the outputs to the next stage. And there are models like this, like pipeline parallel pipeline programs. This is, again, high-level programming model. But this sort of programming model matches nicely the underlying structure of a systolic array. So in this case, basically, you have a loop. You can divide your loop into 3 different code stages, let's say. And these stages are executed sequentially, right? A, B, C, A, B, C, A, B, C, A, B, C. And it turns out maybe you divide your code such that you have very good locality over here. A always executes on some piece of memory. B always executes on some other piece of memory. And C always executes on some other piece of memory. And they actually communicate with each other nicely. And then you keep executing this. So one way of doing this is basically programming this is basically A's are always executed on processor 0, such that you exploit the locality across A's. B's are always executed in processing 1, and C's are always executed in processor 2, right? And people do this actually in pipeline parallel models, assuming you can parallelize it this way. And now you need to communicate between A0, B0, C0. So this looks like a very good systolic computation, right? If you think about it. Let me actually look at this a little bit more. Essentially, we divide the loop iteration into stages. And you could have threads execute stages on different cores. And now I'm generalizing. That's why I'm using this terminology. And the core, or a processing element, can be specialized for the computation that execute on them, right? And then you have basically some communication mechanisms between them. So this is systolic computation if you do this. And this is one example. I mean, there are many examples, actually. Compression, decompression are very good examples for these things. But when you do file compression, for example, assume that you're doing a lot of compression operations and decompression operations. You may ask me when. Video processing is a great example for this thing, actually. If you're YouTube, for example, designing these things, you don't want to do anything in software. You basically do a hardware design. In fact, Google has produced a video engine, which operates somewhat using similarly to systolic principles. I mean, not exactly with this, because this is just my example from 2010 or so. But essentially, you have a lot of files coming through, or pieces of files, and you want to essentially compress them, right? Or decompress them. You can design a systolic hardware that basically does different things in different stages, and each stage can be very, very customized to what you do. This is a software view of things, but you can imagine a hardware view of things also. And if you're interested, I didn't put the slide over here, but Google has a VPU paper, video processing unit paper, in ISCA 2021 that operates on similar principles. Okay. So basically, imagine this happening on many, many files. And that's YouTube for you. Okay. Okay, so I think we've said a lot of this. So I'll go through this again relatively quickly. Essentially, we have a special purpose hardware, which is high efficiency, if you generalize it. And you make multiple use of each data item. You have better use of memory bandwidth, high concurrency, and regular design, which sounds great for a specialized hardware, right? Regular design enables it to be easier to implement, clearly. So the disadvantage is, again, you need regular parallelism, some sort of regular parallelism, and you need to orchestrate the data. Special purpose is not generally applicable. And also, you need software and programmer support to become more general purpose, right? Okay. And if you want to actually fit a problem that doesn't fit, good luck. That's basically the trouble. Sometimes, I mean, even though this model looks nice, for example, partitioning a loop over here, it may not always be easy, right? Especially if you have a lot of dependencies. If the loop is not easy to parallelize, you have a lot of trouble in the end, right? That's where the out-of-order processor, all the data flow paradigms shine, because you cannot parallelize things easily at the software level, or you cannot basically figure out what model fits well. Okay, let me give you a little bit of history. This was developed by H.T. Kung in the 80s, and he was a professor at CMU. And he basically designed one of the earliest prototypes of the systolic array. Let me finish until we get to TP, and then we'll take a break. But basically, I like these works because it's very interesting, early works. And the goal was to really accelerator, very similar to a TPU, as we will see soon. And this was a simple one. And at the time, we were talking about 1980s, right? So everything is big at that time. So the machine is also big. But you have a host machine, and you have a linear array of 10 cells. Each cell is 10 megaflop, which is nothing today, clearly. But it's big at the time. It's also a programmable processor. And they also designed the high-level language and optimizing compiler to program the systolic array to make it easy. for everyone. And the goal was to really accelerate vision and robotics tasks. And they actually had good success. They describe it in this paper. And this is what the thing looked like. It's essentially the systolic array that we've seen, right? And they called it the warp processor. And each cell looked like this. So there's some more programmability, as you can see, right? There's some memory, for example, over here. There's some Q for Y and X. There's some addresses. There's some address generation unit. So there's some add and multiply registers, etc. So basically, if you think about it, it's a little bit more complicated so that you can actually program it. And you can read the paper, which is very interesting. But it's essentially the same idea of a TPU. TPU is actually more specialized. Maybe I'll go through this and then we'll take a break because it's kind of a nice transition. This TPU, when it was introduced in 2017, it's essentially doing matrix multiplication, similar to what we've discussed. The feeding of the data is a little bit different. But basically, if you read this systolic data flow of the matrix multiply unit, and you can see that software has the illusion that each 256 byte input is read at once, and they instantly update one location of each of 256 accumulator RAMs. That's essentially doing what we have seen, maybe slightly differently, but you can read it. Let me see if I won't say anything over here. Okay, I'll let you read it because it's essentially the same concept, but you can read it. So basically what we've seen over here is real today. And this was the first, let's say, big processor. This is a very interesting paper. You can read it right now. In fact, I got to learn that this is the most cited ISCA paper ever in history, even though it was it was in 2017. So it had a lot of impact if citations are a measure of impact, which is interesting. Partly because it's also from Google. Yeah. Okay, anyway. But if you look at this, this is the systolic array matrix multiplication unit. And at the time, it was 64K per cycle. They reduced it over time because they figured out it's better to do smaller matrices and parallelize many of them, which is interesting. So if you read the later Google papers, they talk about that. And it was initially just a systolic array. We'll see in the next version it's something else. But there's a lot that goes into making this work. If you think about it, there's some memory. You need to fetch from DDR3 in the first version into a weight fetcher, and then put the weights inside, and then orchestrate the data. So they actually built a programming model compiler, just like H.T. Kung did in 1980s. Right? That's the beauty of being an academic. I think you envision in 1980s, and somebody builds it 30, 40 years later. Right? So it's good to be patient. He may be dead by then, but H.T. Kung is still well alive. So that's good. Okay. Anyway, you can read more about it. But later, Google improved this. For example, they added more TPU chips. Today, actually, it's much bigger. They changed DDR3. Basically, weight fetching was too slow with DDR3, so they added high bandwidth memory. They added more floating point operations. They increased essentially a lot of things. And they designed for training and inference versus only inference. So this was version 2. Today, we're at version 6, I think. So you can see that they wanted to parallelize a lot of matrix operations. And if you look at each of these, they call it tensor cores, which is unfortunate because they had to clarify it, the block diagram of a tensor core, our internal development name for a TPU core, and not related to the tensor cores of NVIDIA GPUs. Can't you come up with better names? Okay, anyway. I mean, I like this. I'm just joking. It's interesting that two folks come with a same name, right? It's also interesting that these guys want to claim the name after someone else did it. Anyway, they're interesting. But if you look at this, the really interesting part is it's a combination of a lot of paradigms. Now you have high bandwidth memory, and you have a vector unit. This is SIMD, like last week, similar to GPUs. And then you have a matrix multiply unit. This is essentially a systolic array. And the vector unit really controls a matrix multiply unit. What is not shown here is the core sequencer, which is really VLIW. So what we've seen, VLIW also exists in existing systems because their compiler compiles into this VLIW thing. And they don't talk a lot about how they handle a lot of things, of course, but essentially, software managed instruction memory executes scalar operations using a 4K 32-bit scalar data memory. It's not shown here, somewhere, some other figure. And 32-bit scalar registers and forwards the vector instructions to the VPU. So you get a vector instruction inside your VLIW and forward it over here. And then that one can forward it to the matrix multiply units or execute them. So there's some complexity involved. Yes?
But you mentioned that it was better to use multiple smaller matrices for parallels. So
yes.
VLIW just got multiple small matrices
Yeah, basically the encoding of the instruction specifies the small matrices. Yes, exactly. Yeah. Not multiple matrices, but I don't know exactly. You need to go through it. Yes. Yeah. Yeah, but that's yeah.
So one of the questions, this is all going to matrix multiplication, this one
Mm.
tensor core basically, right?
Yeah.
And then what does the tensor core and NVIDIA GPU do? Is that not the same?
So it's a bit different. I think tensor core and NVIDIA GPU is not as powerful. It's really just maybe Mohammed can correct me, but I think a tensor core in NVIDIA GPU does just matrix multiplication, right?
Just multiplication.
Yeah.
And this one is the global.
This one is basically they call it the whole. Let's say I would say this is a much more powerful core.
Okay.
Yeah. It's a bit unfortunate that they both called it tensor core, but I didn't do that. Yeah. And then they connect many of these things. Okay. So later they actually figured out that much you need more memory. So they actually increased the memory. They went to higher bandwidth HBM. They added more matrix units. They increased the processing capability. So basically these things are getting bigger. This is one of the latest one they published on, and you can see that in a single board, you can have 1 exaflops of computation. Again, you can look at these. And if you're interested, they're actually interesting papers. Some of them are hard to read, I think, but you can take a look. Like this one's interesting. This one's also interesting because they actually have optical interconnect to communicate across the TPUs as well. And this is one slide that I just found a couple of days ago on they actually have some versions that they didn't describe, but they keep improving it, as you can see. Okay, this is a good place to take a break because now we're going to deconstruct some of this TPU stuff and show that even though it's actually very efficient at computation, maybe it can be a lot more efficient. So let's take a break for 10 minutes. Let's be back at 17 and we'll continue.
Last night. It's not urgent about the student for the seminar that wants to change the.
Hopefully not today.
No,
Okay, that's good. Yeah.
It's scheduled for 7th of May.
Okay.
So it's been met.
That's what?
The paper been met.
Yeah.
Alongside, I told Mohammed about it. It's supposed to be with SIMDRAM.
Okay.
And she cannot make it.
Okay.
It has like a field trip with a course.
Okay. Maybe we can change it then, right? What do you think?
My note was last night. I mean, I read.
If it's possible to change it.
Is it possible? I don't know.
It's what? Okay. Then we could do it. Yeah.
Okay.
We can swap it with someone else or add it as another presentation sometime. Right?
So we have a session with only one person.
No, we don't have
Not
one
anymore,
with
probably.
one.
We don't.
We have one with 3.
Okay.
So
Yeah.
we can split this and add this one in the. But my question was basically if you want to leave in the middle one session with only one presentation, or we have to move up something.
Yeah. Better to not leave it, or
No, better to not have a session in between with only one presentation. But
I agree. But then someone needs to move, right?
Exactly.
That's
So,
the downside.
so I have to check with people from the last where there are again pin papers.
That could be good. Yeah. I need to check.
Okay,
Pin papers would be good. Yes, I agree.
So it's pin is all you need and facility.
Yeah, I mean those are related to each other also actually. What is facile? It's
I don't know.
okay.
We'll have to check again. But,
Okay.
Okay, then.
I think, but yeah, do something
Okay, so
reasonable.
you
Yeah,
don't
I
have
think
a
it's okay. Yeah,
preference.
it's okay.
Okay,
As long as if you can maintain the topic
Yes.
a little bit, that'd be good. But even if you cannot, what can you do? Right? Sure. We'll do this. Hello. Where are the Greek guys?
Sorry?
I saw them and they didn't come.
Really?
oh, okay.
Okay. Okay, you can, okay, why don't you tell them and ask them?
I will tell them.
Yeah.
Betrayed.
Exactly. Are they
Betrayed
outside?
you. Betrayed you.
Yeah.
No, they betrayed you.
That's true. Yes. Tell them that.
I'm not sure where they are. Then they were setting up their desktops,
Okay.
and
That's not a good reason.
desktop, I think now they're doing progress support.
Oh, okay. They could do it here also.
Yeah,
Yeah.
just let me
Yeah.
let me leave you to them.
Okay.
I'm not gonna add fuel to the fire.
It's not a fire.
We are more loyal.
Yeah, what?
We are more loyal.
Yeah.
Indians, we come everywhere.
He's not Indian. And I'm not
You, both
loyal.
of us,
I
I'm
just
saying.
What's Indian
subscribe.
about?
Yeah, there's a reason why he's here.
Subscribe, I'm not loyal.
Yes, you're this guy.
All right, I'll see you soon. What's up? But Saturday is fully open. I'll schedule many people there.
What?
I think I'll schedule many people there. Including the Greek guys, the traders.
I'm up for it.
Exactly. You can do the progress report. Also, maybe. Exactly. That's the purpose of these. I think it's time. Almost. I think so, yeah. I would like to. I'm going slowly. Yeah, you're going to switch to it at some point. Yeah, yeah. We'll see when we get to it. Are we online? All good. How about now? You can? Yes? Okay. I don't know about online. Okay. If it's working, let's continue. Okay, so we basically covered systolic arrays, and you can see that it's actually interesting. I think machine learning acceleration uses systolic arrays at the core of the matrix computation, but you also have other paradigms surrounding it and controlling it. So existing machine learning accelerators consist of multiple paradigms, SIMD plus systolic, and some include VLIW also, which is interesting, I think. But let's deconstruct it. So this is a study that we did with Google, especially for edge models. I'll go through this relatively quickly to especially foreshadow what we're going to discuss later. What is the future, basically? So if you look at a Google Edge TPU, essentially, when you so Google released the cloud TPU versus Edge TPU. Edge TPU is very specialized for edge devices. Like if you're in the field, let's say, and if you want to do some machine learning inference, this is a smaller version of the TPU, essentially, with much lower energy and cooling requirements. And we analyze this for edge machine learning models that are used at Google at the time. This is a paper that summarizes a lot of the results, which is very interesting, I think. But essentially, it's very memory bound. And this is going to be what we'll discuss later, more futuristic models. So if you analyze different models that are executed, some of them are CNNs, some of them are transducers, LSTMs, etc., long short-term memories. Especially on large models, if you characterize the energy consumption on this edge TPU, you see that most of the energy is really spent on going to DRAM and off-chip interconnect to get the input data and to get a lot of things, essentially, parameters. That's true for other models also, but not as dramatically, let's say. Okay, so basically, there's a lot of analysis in the paper. Essentially, the edge TPU or a TPU is a one-size-fits-all accelerator. Whereas if you look at these models, this is looking at two different metrics for each model layer. In this case, for different models. On the y-axis, we have arithmetic intensity, flops per byte. On the x-axis, we have parameter footprint, essentially how large are your parameters, input parameters to the model. And you can see that there's a huge difference, huge spectrum over here and a huge spectrum over here. Some of these models have, some of these layers have very high arithmetic intensity, very low parameter footprint, great fit for a TPU. So this area is probably not a bad fit for TPU. But if you go to this area, you have very little arithmetic intensity. You do only one flop per byte. And your parameter footprint is very large because of the way models are constructed. Of course, you could improve arithmetic intensity with some techniques as well, but this is what we had at the time. And basically, if you look at a single layer or single model within each model across different layers, you also have a lot of variation. This is the multiply and accumulate operations. So there's a huge variation, as you can see. This is the arithmetic intensity. There's also a huge variation across different layers. The question is, does it make sense to have a single accelerator to cater to this huge variation inside the models and across the models? And the basic idea here is basically no. Instead of designing a monolithic accelerator, we could design a family or different types of accelerators to cater for different types of families. And in this particular case, we kept a very lean version of the edge TPU to handle compute-centric acceleration, meaning these are the things that don't have a lot of memory intensity. And you can simplify this a lot. This is one of the reasons they make the TPU bigger is because they cater for memory intensive parts. But if you actually design an accelerator only for compute intensity, you don't need to have a huge, let's say, memory, for example. And you can reduce the array size also. So basically, that's the idea. Again, we may go into this when we talk about memory-centric computing. And we also designed 2 other systolic arrays in the 3D stacked DRAM, very close to memory, so that we can actually do more data-centric acceleration for layers that have a lot of memory intensity, very low arithmetic intensity, for example. And you have a scheduler that schedules the different models and layers to different families. Okay, so if you do that, the question becomes, how do you identify the families? You can do this classification online or offline. Again, based on the arithmetic intensity we have, parameter footprint we have some classification of these different layers into compute-centric versus data-centric, and then we ship them to different accelerators. And if you do that, you get actually significant energy consumption reductions, improvements, and also throughput improvements. Again, I will not harp on these numbers. You can read the paper for more detail, but you can customize a lot more. And these are, we're still using only systolic arrays. So systolic array, compute-centric systolic array, and 2 data-centric systolic arrays. They're data-centric. They're 2 different ones because we try to cater for different types of intensities and different types of data flow. Hopefully this is interesting. So this is a more researchy thing, as you can see. It's always good to ask the question, is this enough, right? Is this good enough? That's how you make things better, by questioning things. Okay, I think these guys also asked the question, like, is this good enough? And they came up with a very different approach. I think Mohammed discussed this last time, but I'm not going to go through it in detail. Essentially, they have a wafer scale approach. So they have a huge chip like this, which is a lot of implications, of course, on cooling, reliability, etc. But their main goal was to actually overcome the memory bottleneck that we also discussed, right? Essentially, they wanted to put a whole lot of compute together with as close as possible to a whole lot of memory. In the end, it's a different approach for executing matrix multiplication or neural networks. So they have a MIMD machine, as we have seen last time, and each MIMD machine consists of SIMD processors. So this doesn't have systolic arrays, but it could. Essentially, if you want to be more efficient in the computation, maybe you have a systolic array. You still have the MIMD, SIMD, and systolic array paradigm. It's possible to do it, right? They just, at least so far, based on what they exposed, they didn't really do systolic arrays inside their system. Okay. Okay, there's more on the topic. So I think Mohammed left with the slide, but last time it may not have made sense. Right now, you know GPUs and systolic arrays. There's also FPGAs, which I'll have one slide on, and that'll be the last slide. So the question is, which one's better for machine learning? Which one's better for different workloads? What types of parallelism, or what type of parallelism does each one exploit? What are the trade-offs? I will not answer any of these, but these are actually really good questions to ask. And these are questions people are asking in the field also. And you can see that it's kind of a mix of different models that people employ today to do the best. People have used FPGAs also for neural network acceleration. This is a nice paper from Microsoft on using FPGAs. They call this Project Brainwave, so that they can accelerate computation. Again, basically, they map matrix vector multiplication into hardware directly. I mean, you could implement a systolic array on an FPGA also, right? You could implement a GPU on FPGA, but they actually implemented this directly. So if you're interested, you can take a look. Of course, FPGAs have other implications as well. They're quite generally reconfigurable. So maybe the implementation of this on an FPGA is not very efficient, right? But I think internally at Microsoft, this had a lot of impact. I don't know if it's still used. It may not be the most efficient implementation in the end. Because of the very general purpose design of FPGAs today, right? If you design a systolic array just as for matrix computation, it's very different from configuring lookup tables and connections in an FPGA, which has a lot of overhead, right? And if your goal is maximum efficiency and maximum performance, FPGA is a lot of things that are, let's say, that are controlling the reconfigurability, right? But they have interesting results. Okay, so that brings me to the end. Any questions? Any other questions on systolic arrays? We can overlap some latency. Or is it easy to find where it is? Okay, I see myself. Oh, is this correct? That's 9A. Okay, I'll let you find 9B. Maybe somewhere else. How did it come over there? Magic. Share, I think. Did you share? Okay, you share afterwards. Okay, we have 34 minutes to cover simulation. Clearly, we're not going to cover everything in simulation. But it's important to discuss this because you're going to do some more simulation for your later labs. I don't know if I'll be able to cover the emulator, but let's see. Okay, cool. Thanks. Well, you've been doing simulation, so but I think it's a more formal lecture on simulation. And I like this because this is really where you can invent new things and how you can really explore new ideas, I think. You cannot implement hardware for everything, right? So every idea you have, if you had to implement hardware, you would be very limited to idea throughput, right? Your idea throughput is very low in that case. And there are things that you cannot test in real hardware. How do you test them? Like if you have some futuristic idea, like a systolic array, initially you may not be able to implement hardware, but you test them in simulation, right? Okay, so I'm going to focus on memory systems especially, but that'll come a little bit later. So the question is, how do we evaluate new ideas for new architectures, right? Another way of asking this question is, how do we assess how an idea will affect the target matrix X? Right? So there are many potential evaluation methods, some of which are not used as much in architecture when you design a new architecture. One is theoretical proof. Depending on what you are investigating, what X is, this may be difficult, especially for performance, energy consumption. This may be difficult. It may be okay to prove some security characteristics, etc., for example, but theoretical proof is usually much tougher for performance energy evaluation. Analytical modeling and estimation, you have some analytical model that you design, and based on some assumptions that you make, you can guess what the performance could be, what the energy could be. This could be useful for regular things. So if you have very regular computation, for example, matrix multiplication, with some assumptions, you can perhaps get some good analytical model that describes a hardware, right? Maybe a systolic array. I don't know. Looks like we have more visitors coming. Magically. Magic. Yeah, okay. And simulation, which is what we're going to talk about, is you can do this at varying degrees of abstraction and accuracy. But they missed the systolic array part of the lecture, which was arguably the more interesting one. But I like this one because this is also going to enable other ideas. So basically, you can do this at varying degrees of abstraction and accuracy, and that's what we're going to talk about today. But there's also other things that you could do. You could prototype with a real system. For example, FPGAs are very good for this purpose, I think. You can do a lot of prototyping of new ideas. Again, depends on the idea. If the idea is completely, let's say, different, you may not be able to get the benefits on prototyping. You may get close enough, maybe. So there's a danger of evaluating new ideas with existing hardware, right? That's always because what you're envisioning is a very different hardware. If it could be done with existing hardware, then you could do it. So evaluating very different new ideas with existing hardware is usually difficult. Okay, and then you could go and really implement your idea. And this is, of course, probably the most expensive way of testing your idea. And if you fail, and also it takes a long time to do this real implementation, right? So anytime I have an idea, which one do you use becomes a question. And usually, especially with forward-looking ideas, you need to do these two, probably, analytical modeling and simulation. I'm going to talk about simulation, but analytical modeling is increasingly important too, but it has a lot of limitations in terms of what you can model over here. Okay, but let me talk about a prototyping platform. So this is something that you can use clearly for some things, right? And we actually have a lot of prototyping platforms using FPGAs to test DRAM chips. And this has a lot of benefits. We have a lot of papers. I'm not going to talk about them right now, but maybe in a future lecture we'll discuss. So these are a lot of FPGAs connected to a PC, and FPGAs do something. Testing memory chips is one example. We released the SoftMC infrastructure, which is actually a programmable memory controller where you can test DRAM chips. You can read papers about it. There's also a newer version of this DRAM vendor with multiple FPGA prototypes. In fact, there's an HBM prototype also. Essentially, you can test the DDR3, LPDDR, DDR4, HBM chips. And what is this useful for? Basically, discovering new things, like RowHammer, figuring out different kind of error mechanisms. And these are some papers that I will not go through right now. Discovering new problems. And I like this actually because by doing this sort of prototyping, you can discover new things that other people may not have discovered, right? So that's the benefit of, I think, prototyping or designing platforms that could be useful for understanding what already exists. We also discovered like you can actually do bitwise operations in DRAM by violating the timing parameters. We may again talk about that later on. And you can do simultaneous row activation, row copying inside real DRAM chips, commodity DRAM chips, without changing the DRAM chips, which is also interesting. And more recently, we looked at other read disturbance issues, which make things much worse. So you can study a lot of interesting things with real prototyping platforms also. So this is not to mean that they are not useful. They're very useful, but it may be very difficult to use this sort of prototyping platform for some other purpose. So it all depends on your purpose in the end. If your purpose is to come up with a completely different architecture, maybe this is not easy on a prototyping platform. Okay, so another thing that you could also do with prototyping platforms is you could do more end-to-end evaluations if it's possible to do. So in this work, we introduce a FPGA-based framework. And the idea is to hopefully evaluate some end-to-end applications if you can port to it. So what this FPGA has is a RISC-V processor in it. It is a memory controller. All of them are memory controllers programmable. Essentially, you can run a full application, a full operating system. And the idea is whenever the RISC-V processor executes a memory copy instruction, it ships it to the memory controller. And the memory controller copies the data internally inside the DRAM without actually bringing any data to the processor. So we do memory copies inside DRAM. We're going to maybe talk about that later on. But you could do some things in real prototypes. And this is actually very useful. And the reason you could do it in this case is because we could violate some timing parameters in DRAM so that you can do back-to-back row activations in a single subarray and do the copy. So there's a lot of interesting things over here. And this may become more interesting later on when we talk about memory-centric computing. So there are limited things that you can do with real prototypes, even with like looking at emerging paradigms. There's another thing that this does, which is really generates random numbers. So when the application has a random function call, we ship it to the memory controller. Memory controller violates some timing parameters in DRAM and produces random numbers because violation of some timing parameters leads to some cells to fail randomly. And if you can actually identify which cells fail randomly, you can have a random number generation inside the DRAM chips. And then you can supply that to the program that's running on the RISC-V processor. So you could evaluate some things, assuming you can do it in existing hardware, which is also fascinating. Okay, so if you're interested, there's a lot of all of these tools are open source and you can find them. And we actually, these are real results. This is basically copy and initialization throughput. If you do it by offloading copy and initialization to the memory controller, you improve throughput significantly for these micro benchmarks. And the reason is this RISC-V processor is a wimpy, very simple processor. If it was actually like if it were using all of the techniques that we developed in this lecture, out of order execution, etc., tolerating latencies, then this number would go down by an order of magnitude. But still, you would get a lot of benefit. Okay. So basically, you can benefit from real prototypes. But the difficulty in architectural evaluation is really, there are many difficulties. One of the difficulties, the answer is usually workload dependent. Caching, for example, pipelining. Any idea we talked about? Well, we didn't talk about some of these, but this is a slide from some other lecture. But we're going to talk about some of these later on. Workloads change. Essentially, you may say, OK, I want to evaluate these workloads, but 5 years down the road, workloads may change, right? You may design, for example, for machine learning inference, but then training becomes important, and you may need to design something else. Your workload may be a neural network, but later it could be an LLM. And 10 years down the road, hopefully it's not a dumb LLM. Hopefully it's a much better thing. And system has many design choices and parameters also. And so basically, as an architect, you need to decide many ideas and many parameters for a design, right? So it's not easy to evaluate all possible combinations in the end, right? And system parameters may also change, right? So there's a lot of things that may change in the end. And I think if you design a good simulator, you can explore a lot of these. So I call this field of dreams. So essentially, if you're an architect, if you're designing a new chip or new idea in a research, you're really dreaming. You're trying to create something, right? And simulation is, I think, a key tool of the architect because it allows the evaluation and understanding of non-existent systems. It enables you to explore many dreams, potentially. It gives you a reality check of your dreams also, if assuming that you design the simulator reasonably. It enables you to decide which dream is better, which is nice, I think. But it also enables you to fool yourself with false dreams or bad dreams, let's say. So basically, if you don't have a good simulator, you may actually make a bad decision, right? So that's why I think this is really an interesting topic. And design of simulators is really important for enabling the good things while hopefully avoiding the bad things, right? Okay, so we're going to talk a little bit about high-level simulation. The simulation happens at many levels also. Like if you design RTL code, for example, register transfer level, Verilog, and then you simulate it, that's one level. There's a lower level. You can actually have circuit simulation, right? You don't have to stop at RTL, right? Why not look at all of the circuits and look at all of the analog, simulate everything in analog, right? You could do that also, except it's much slower. So basically, as you go into lower and lower levels, you become slower and slower. High-level simulation is faster, and that's one of the benefits. Basically, low-level simulation, RTL is one example of it, but there are actually lower-level simulations also that you could do, is intractable for design space exploration. It's too consuming to design and evaluate, essentially, especially when you have a large number of workloads to test. Especially if you want to predict the performance of a good chunk of a workload in a particular design. Basically, it takes a lot of time to actually simulate, especially as your RTL code or processor gets more and more complex, right? And if you want to consider many design choices, so a lot of things multiply in the end. And this is just an example from caches, right? There are many things, even in a single cache. And then there's memory controllers, there's in-order versus out-of-order execution, there's reservation station sizes, most store queues, etc. So you don't want to basically do a very slow simulation to decide things. Basically, our goal is to explore design choices quickly to see their impact on the workloads we're designing the platform for. So that helps. That's where high-level simulation is very beneficial, right? And then there are many goals in simulation also, right? People use simulation for many reasons. One goal is to explore the design space quickly to see what you want to really implement, right? Potentially implement a next-generation platform. Or propose as the next big idea to advance the state of the art. In both cases, you really want a quick design space exploration. But maybe in research, you want an even quicker one, right? Because you're really exploring big things that are harder to even implement in RTL, right? If you come up with some new idea, how do you implement an RTL to begin with? You have to explore a lot of things with it. So the goal here is to mainly see the relative effects of the design decisions. The goal is not to really fine-tune, oh, if I do this, I get 0.01%, right? That's not the goal over here. But there is a case where that goal is also important, where, for example, you design a simulator to match the behavior of an existing system. You implemented a processor, the best processor of its time, let's say, and then you want to calibrate your simulator so that you can actually debug and verify it at the cycle level accuracy. And so that you can propose small tweaks to the design that can make a difference in performance energy, right? So here you're operating at with a very different goal. And the goal in this case is very high accuracy in the simulation, hopefully, right? Because you want to match the system and you want to understand its bottlenecks in simulation because you don't have enough visibility into the real hardware that you implemented. But in a simulator, you can modify things and see that visibility, right? If you match the system's behavior, then you can actually do a lot of interesting things still over here. And this is very useful for designing the next generation of your processor, for example. There could be other goals in between, actually, and there are other goals. You can refine the explored design space without going into full detailed cycle-accurate design so that you can make the next level of decisions. You can gain confidence in your design decisions made by higher level design space exploration. So usually you have a progressive refinement in simulation. If you go design hardware, there are some simulators that are very high level. They could be merged with analytical models, actually. And these give you like high level things. And then there's a next level of simulation that's a little bit more detailed. And then there's next level of simulation that's a little bit more detailed. And then you have RTL at the bottom. So you progressively actually go from the highest level to the lowest level when you're getting closer to releasing a product, clearly. But also, having these different levels of simulation enables you to, and in the end, real hardware enables you to go back and fix the simulators, right? So it's a nice loop. And if you have a long tradition of designing processors, you can actually fix a lot of things, make your simulators much better over time. Make sense? Okay, so essentially, there are trade-offs in simulation. And usually there are three metrics, or at least three metrics to evaluate a simulator. How fast your simulator is, how flexible it is, and how accurate it is. Right. Accuracy may be tough if you're looking at a future system, right? But basically, how fast the simulator runs, it could be measured in different ways. This many instructions per second I can simulate, this many cycles per second, or this is the slowdown compared to a real system. How flexible is, how quickly can you modify the simulator to evaluate different algorithms and design choices? And accuracy is how accurate are the performance energy numbers versus a real design. That's also called simulation error. Okay. And the relative importance of these metrics varies. It depends on essentially where you are in the design process and what your goal is, clear. Right? Maybe I don't care about speed as much, but usually you do. Usually you have a requirements with these, and usually you can get 2 of these and not 3 of these. This is one of those things where you can get 2 of these. Can you get all 3?
I think if you get the second one, there's a high chance you get all 3.
If you get the second one, flexibility, you get all 3.
Yes.
Good luck. Okay, we'll need to look at that in more detail. I think it's tough. Maybe he's going to give a lecture on how he gets all 3 later, not right now. Okay, basically, it's usually a trade-off. For example, speed and flexibility affect how quickly you can make design decisions and trade-offs. Accuracy affects how good your design decisions might end up being and how fast you can build your simulator. So simulator design time is another metric, basically. How fast you build your simulator. In fact, this is really important because if you're designing a relatively different architecture, and if you don't have a good simulator for it, you may not be able to start, right? And this is what happened to Intel a while ago when they were moving from Pentium Pro to Pentium 4, for example. They didn't have a very good simulator for Pentium 4. And eventually, some very smart simulator designer architect came and fixed it. So they didn't have a disaster. Today, they have other disasters. Not related to simulation, I think. Okay. So flexibility also affects how much human effort you need to spend modifying the simulator. That's also important, right? Because if it's not flexible, and if you want to really look at an idea, then you may actually need to go and spend a lot of effort to change the simulator. Right? Okay, essentially, you can trade off between these 3 things to achieve design exploration and decision goals in the end. And I don't believe you can get all 3 at the same time. Depending on what you define as accuracy, right? If you can tolerate some inaccuracy, you can maybe get 3. Okay, so high-level simulation. The key idea is to raise the abstraction level to give up some accuracy to enable speed and flexibility, and hopefully quick simulator design, right? So the advantages, I think we kind of talked about it. You can still make the right trade-offs, hopefully, and can do it quickly, right? All you need is modeling the key high-level factors. You can omit corner case conditions. That doesn't happen, for example, a lot. And that's actually a good start. What happens and what doesn't happen. As long as you make a good decision of that, you can get rid of a lot of things that are not needed to be modeled, at least initially, right? So all you need to get at this level with high-level simulation is to get the relative trends accurately. You don't need exact performance numbers. Maybe like if I have idea A, idea B, I don't care if it's, I only care that A should be much better than B, right? As long as I get that right, maybe I make the right decision. Right? The disadvantage, of course, yeah, you may make the wrong decision if your simulator is not good enough, right? So that's always a danger. And it's always good to know that it's a danger and be very careful in designing a simulator in terms of what you can omit, what you cannot omit, for example. For example, if your workload has a lot of TLB misses, and if you don't model the TLB, you may be in for trouble, right? So virtual memory performance can be important, and you can talk to Konstantinos about that. So basically, how do you ensure you get the relative trends accurately, right? So I mentioned this earlier, but I view simulation as a progressive refinement. You start with very high-level models, and then you develop medium-level models that are less abstract. You go to low-level models, and then eventually you get a real design, right? Hopefully, at some point. As you refine, abstraction level reduces. as you go from basically top to bottom. Accuracy hopefully increases, but not necessarily. Again, if you're not careful. There are actually very interesting works that sometimes appear, and they show that, oh, if I can model things at a higher level, abstract level, I actually get less error. Because sometimes I make the wrong things over here when I model things low. So maybe that's what you're thinking. That's possible. But when you go from the top to the bottom, your flexibility reduces. And let me give you one example of what I meant. So you model energy, for example, right? One way of modeling energy is modeling everything that happens and taking the energy of looking at how many times you exercise each component, and then multiplying the times you exercise each component by the energy consumed to do that sort of exercise, like accessing, for example, using your ALU, for example. You can multiply it with some energy, add to it how many times you use your floating point unit and the energy associated with it. Add to it the caches. Basically, you do all of those, a lot of accounting. And in the end, you get an energy number, this many nanojoules. Right? An abstract model may do none of that. It basically looks at IPC. This is my instructions per cycle, and this is my average energy. And that may be more accurate, because assuming you get a good average number, right? In the end, a very detailed model needs to have very good numbers and very good modeling of a lot of things. But an abstract model that's tuned based on a lot of data can be potentially better. And I think I have seen this many times with energy, especially. Okay, but it doesn't mean that that's always the case. If you do everything right, the intuition says that lower levels should give you better accuracy. Okay, flexibility also reduces as you go from top to bottom, but speed likely reduces. Well, speed also reduces probably, but except for real design. Real design speed is probably faster. Right? So once you get to real design, then you can run programs and you can get real numbers. And then you can start tuning the other models, right? Okay, so you close the loop, basically. Once you get to a real design, you can close the loop. Otherwise, you're completely open loop, right? Okay, basically, you can loop back and fix higher level models. Okay, so I think making the best of architecture is really being comfortable at all levels of refinement, which is very interesting, including analytical models. I didn't include analytical models, but high-level models can include analytical modeling as well, so including the extremes. It's good to know when to use what type of simulation, and more generally, what type of evaluation methods, including prototyping. And again, there are a variety of evaluation methods available, right? Any questions? Okay, I'll go through some general issues in architectural simulation, but I'm not going to go through everything over here because there's a lot over here. But again, in the end, goal of simulation dictates many things. It drives many design choices on what simulator to build or use. And remember the metrics. And there are many possible goals over here. Entire system performance estimation, component performance estimation. You just do profiling for statistics, understanding bottlenecks of an existing system. These are some of the things that I added over here. And in simulation, just like in prefetching, there's what, how, where, and when. What do you simulate? Do you simulate a component or the full system? Do you simulate programs or traces? How do you simulate it? There are many choices over here. Functional, timing, event-driven, cycle by cycle. How do you do state maintenance and recovery? Again, I'm not going to go through all of these design choices. Unfortunately, we don't have time. Where do you simulate? Do you simulate in software, or do you actually use hardware acceleration? It's also good to think about that, right? You could simulate using FPGAs, for example. And when do you do things in simulation? So when you go into the guts of simulation, you could actually play a lot of tricks, because in the end, you're simulating a program, and you could execute that program and figure out what the program is supposed to produce. And you have actually a lot of Oracle information. You take an instruction, let's say, you execute it at the front end of the simulator, and you know exactly what will happen with that instruction. And then you can model the timing of what happens based on that information. And you could actually do a lot of interesting studies, like if I actually had a perfect bench predictor, this is what the performance would be. If I actually had a perfect cache, this is what the performance. Or you could execute completely like a real machine. Okay. So the inputs can be also varying. So the simulator can take as input program binary, or multiple program binaries. It could take as input system state or checkpoint or some sort of trace. So there are a lot of options over here. The outputs can be functional, program results, and statistics about functional execution, or you could have timing related outputs. These are performance. And then there's energy, of course, right? For example, you can get the execution time in each program, system throughput of all programs, and many statistics about timing and performance events. I didn't even include energy over here, but there could be many, many things over here, clearly. So these are some issues. Again, we don't have time to cover everything, but functional simulation essentially simulates things functionally. Like what should the results be, right? And this is good for example, verifying in instruction set architecture. Right? This is also good for integrating to a timing simulator. So timing gives you timing. You execute a full system versus component. What do you really want the full system sometimes, or do you want to just model memory, for example? What should be modeled becomes important. Do you model the operating system completely? Do you model the virtual machines? Do you model the memory allocator? Konstantinos does a lot of work in these areas, so you can talk to him. If you're interested in doing research in this area, he's the one to talk then. He probably has the magic of flexibility, accuracy, and speed, which I'm going to ask about later also. Okay. Do you simulate a complete workload, or do you sample pieces of it? How do you form the workloads to simulate? What parts to simulate? There are a lot of interesting things over here, and people actually looked at a lot of different ways of doing it. Because if you simulate a complete workload, it could be very long, right? Even if you do high-level simulation, right? Forget about RTL. Because modern workloads have trillions and trillions and trillions. Like if you look at machine learning training, right? Even on a real machine, this takes days, months. Imagine simulating it with a 10x slowdown. 10x is not slow, actually. Now multiply that by 10x. That's not good, right? Multiply that by 1000x, that's terrible. You will never get a result, basically. Well, never is probably too strong, but you will not get a result for several years, maybe. Okay, so basically sampling is important, or figuring out what to simulate and how to project the performance from smaller pieces of a program is important. Warm-up is also an important issue, right? How do you actually warm up simulated structures, caches, branch predictors? What do you simulate? What system state you simulate is important. Okay, again, there are a lot of questions over here, but we don't have a lot of time. But this is just to give you an idea of a lot of the issues over here, right? This is actually a simulator that was used very popularly in computer architecture. It's called Simple Scalar. You may have heard of it. How many people heard about that? Okay, there's one person. Okay, more than one person. It's not used that much anymore, but it was actually a very simple way of modeling, at least the core of a system. You can see that there are different, even within that simple model, there were even simpler models. For example, there's a functional model over here. There's some functional model with some safety checks, etc. There's lots of statistics enabled. There's some cache statistics enabled, cache simulator, and then out of order simulator. So you can see at the time, this is old, it's an old slide from Todd Austin, who was one of the developers of the simulator. You can see that the number of lines is actually very small compared to a real processor today. But this was used for a lot of architectural studies at some point. It didn't have a very good memory model. It didn't model, at least the initial models were actually, this was very core-centric. If you actually had a lot of cache misses, the model was actually pretty bad. So think about that also. Maybe you don't model a lot of components. So I think there are a lot of papers that reached wrong conclusions, especially when programs are memory bottlenecked. Okay, so your simulator may actually affect other things, as you can see, right? If you use a simulator without really understanding what it does. I don't think this is an inherent problem with the simulator. This is a problem with the use of the simulator, right? You should not take a simulator and use it for a purpose that it's not modeling. I don't take, for example, some simple scalar and model details about how the memory system should be designed. That's a bad idea. But people may do that, and maybe that's their fault. It's good to think about that, right? So don't use anything out of its purpose. You need to really understand what's going on in the simulator. Otherwise, if you take it as a black box, you can feed programs and get outputs and modify some things maybe. You may reach completely wrong conclusions. Okay, so there's also functional versus timing. I think I'm going to skip this, but you can take a look at it because we don't have time. But this is another example where people use FPGAs. So you could actually implement some of the timing model in the FPGA. Essentially, you have a functional model. Functional model put the traces, provide some traces. In the FPGA, you have a timing model of an out-of-order processor, and you accelerate that timing, for example. You accelerate the cache simulation, for example, by exploiting a lot of parallelism over here. You could do this with a GPU also, but so they're interesting things. You can read papers on this topic also. Okay, there are more issues like validation of accuracy. How do you validate the accuracy? This is always a problem. What do you validate against? Do you validate against a real system? Okay, you could do that, but what if that's not your purpose? What if you're designing systems 10 years down the road? A completely different system, like processing inside memory, right? Well, what do you validate against? It doesn't exist. So you need to think about that, I think. And a lot of things are enabled by this sort of thinking, basically. I don't want the existing system. I want something different. And that's how we get to out-of-order execution, right? If you look at original out-of-order execution papers, they don't even have a lot of numbers. This is the system that I want to design because of these principles. And later they simulate. And over time, basically, there's more evidence that this is a good idea. And then at some point, it's implemented, then you can validate. That's the point when you can validate. And even what you validate is a particular implementation of the idea, right? It's not really the idea itself in the end. Okay, or the general idea itself. Accelerating simulation, people have looked at this a lot. Like we have software matters, better software engineering. That's really important, but also hardware support. Hardware support, of course, if you can do that, that could be very useful because now you may actually have a prototype. I thought I was hearing myself. Trace-driven versus execution-driven. Again, you can capture some trace and you drive what is modeled in simulation. Or the simulator itself executes the program and determines what is executed. So if you actually execute the program, you can model some things more easily, potentially, like wrong path, right? If you actually have a branch misprediction, if you execute the program, you could steer the program to the wrong path also and see what happens in the wrong path, right? But if you don't execute the program, if all you have is a dynamic trace that you captured after the execution of a program on a real system, you don't know what to execute on the wrong path, right? Because the system didn't go to the wrong path, because you cannot capture it unless you capture a wrong path trace, which many systems you cannot capture that thing. Okay, there are other details, but I will skip this one also, right? There's a lot of interesting issues, basically. How do you do state maintenance and recovery? How do you model mispredicted execution? What kind of like simulation? Do you do cycle by cycle simulation? Every cycle you simulate everything, which is very, let's say, not scalable. Or do you do event-driven simulation? Basically, you have some event queues, and whenever an event happens, you launch some part of simulator. Okay, let me go through an example simulator, and then we'll be done. This is good because I have only 2 minutes, and I can do it in 2 minutes. Let's see. But this is a simulator that you're going to use, I think, in a later lab. Is that correct? Okay. Basically, this is a simulator that we developed because we felt that it was missing in architecture. And the idea, it's a RAMulator, so it's a RAM simulator or DRAM simulator, or a memory simulator in general. And at the time we developed it, this was actually based on our original simulators from 2006 that I developed or co-developed at Microsoft Research, and we extended it with my students. And eventually we decided to release it to the community. Essentially, DRAM landscape is changing. There are new memory controller designs that are produced, and we wanted a fast and easy to extend simulator for modeling all of these different types of DRAM. We're going to talk about memory and processing in memory later on, but this is a fascinating landscape. People have been developing a lot of new DRAM interfaces and new ideas in DRAM. And our goal was to actually provide support for many DRAM standards, and RAMulator provides that support. We have a new version that provides better support, let's say, and also be as fast as possible. At least the initial RAMulator was 2.5x faster than the fastest open source simulator at the time. And we also wanted to be more modular and extensible. Now, initial RAMulator is still more modular and extensible compared to other simulators, but the new RAMulator is much, much better from that perspective. And this is the kind of studies that you can do, for example. On spec workloads, on some workloads, you can basically run programs and you can test many different types of DRAM. And you can see what kind of performance you get. For example, in this case, we showed that if you use DDR4 instead of DDR3, you get a little bit of performance. If you use HBM instead of DDR3, you get a lot more performance. In some applications, you get a lot more performance because they need a lot of bandwidth needs. If you use LPDDR4, you lose some performance, right? So you can actually do this sort of studies. These studies you cannot do on a real system because there's no real system that has all these memory interfaces. Good luck designing something like that. That'll be the most expensive system of the world. Okay, so this is RAMulator. This is the paper and the source code. And you're going to look at it. It's integrated with other simulators, but we have a new version. Well, we have a RAMulator project course also. If you're actually interested, you can take a look at it online. But RAMulator 2 improves upon RAMulator to make it more modern in the sense that it uses better software engineering principles. Like this is released 8 years after the first DRAM later. It also uses like a lot of features of the C++ language. It's also more modular and hopefully better extendable. So if you're interested, well, it will not be a bonus assignment, but it will be a real assignment. But you can also review the RAM later and RAM later 2 papers when you actually do your real assignment. Okay, so this is a great place to stop. We'll pick it up next week. Oh, not next week. Next week is Easter. Okay, yeah, not next week. Next week, basically. So yeah, you can rename next to next automatically. All right. I'll have a good Easter break, and we'll see you in 2 weeks then.